It's lecture 4, and we're enjoying ourselves learning about math and probability still. And we'll have one more lecture after this doing probability, and then after that we'll get into the, I guess, fun stuff, the purpose of the course. So a little more struggling with this stuff. Before getting into this, I guess I should mention there's assignments in this course, as you know. And the first assignment is going to be released tomorrow. So like 3 of the assignments you're going to have are programming assignments in these Google Colab notebooks. The programming assignments are going to come kind of later in the course once you actually have something to program. And so the earlier assignments, I guess, are going to be mainly these kind of like math and theory style questions about course content and so on. And they're all just going to be like quizzes on Canvas that are like these multiple choice questions that you do the work, you submit the thing, and the quiz is open for like a week. So you can keep coming back to it and updating your answers. And there's like a PDF that also has all the questions, so you can work on it offline. And yeah, they really shouldn't be too challenging. And yeah, it's mainly to just like force you, I guess, to keep up with the course every week. Okay. So shall we begin? Yeah, so let me quickly remind you what we're doing. So we had this situation again, we want to do supervised learning, we have data, it's a data set, and we said, okay, like where's our data set coming from? And roughly speaking, we wanted to say something like, it's randomly chosen, you know, like if you were collecting houses, you just like randomly send out some survey or something and gather this information. And then since things are random, you're probably gonna want to talk about, well, like, okay, based on this randomly chosen data, like, what can I expect my learner to do? Like, is it always going to output something good? Well, that's probably going to depend on the data. So maybe instead of like talking about, does it always output something good, as in like a good predictor, maybe we should talk about like, does it output something good on average? Or like things like this. So that's why it's all going to be kind of important. And then we got into all this probability stuff. And walking to this class, I realized that maybe like some of the intuition was missed, or maybe things got confusing. And so maybe instead of jumping straight into the notation and stuff, I decided on the way here that maybe like a fun, motivating example could be good to go over. So we're gonna try to like go off-roading and do some live explaining of something I came up with on the way here, and we'll see how this goes. And if it confuses you, then maybe just forget about it, and we'll continue with the technical stuff in like 15 minutes or something. So shall we get into it? So here's the idea, like, you know, you want to like things, somehow you're getting these, like you're running some experiment, you're getting some random outcomes and so on, and like you somehow want to talk about like what's the probability of something happening and things like this. And we're going to think of it like, maybe like this. So like, suppose you had this like infinite kind of like number line. You can think of it like you have an infinite rod, and it has like no mass, right? It's just completely weightless, let's say. So there's like no weight on this rod, and you somehow, like your goal is going to be somehow to like assign a total weight to this rod of 1. Okay? And the way you're going to do this is you're going to put like mass, like point masses on the rod, and you're going to need that the point masses kind of sum to 1. And so like these point masses, we're going to call them probability world, the outcomes, and like the mass, we're going to call the probability of that kind of outcome, roughly speaking. So let's start with like some set of, I don't know, like points we want to populate on this line. So maybe we want to populate the locations like 1 or 0 and 1. All right, so we're going to put some mass on these 2 points. These you can think of as like, you know, if this is the in negative infinity to positive infinity interval, we're going to put some weight on the 0, 1 locations, and let's say this is like 0. So that we ground ourselves. And so like, we're gonna need to put a total mass of 1. And mass should be like related or synonymous with the word of like probability. So we're gonna try to assign a total mass, a total probability of 1. And so like if these are the points 0 and 1, okay, let's put some mass on 0. Maybe I put like, this is like my mass. And I put another amount of mass on like 1. And like visually you can see they're probably like around the same weight. So let's somehow give them a measurement, and I'm going to define a function that tells me how much mass I have as this like probability distribution. And for now, like, let's just say you can take in just like outcomes. And so like this might take in like, let's say 0. And it's going to have to give it some probability or some mass. And just like visually, since things are going to need to sum to 1, and like these masses kind of look the same, maybe I give it like 1/2. And then the mass of like, I don't know, the 0.1 on this infinite rod is going to also have 1/2. And so this sums to 1. And yeah, so the constraint you're going to kind of have on this function is going to be that like, you know, if you take every single possible outcome, somehow, imagine you can like maybe pass it in like this for now. Somehow that's supposed to give you 1. Right? So that's like, that should be kind of intuitive. And what does this map to? This maps to like your flip of a coin, a fair coin, where like the probability of getting, let's say, tails is 1/2 and heads is like 1. We've mapped the numbers 0 to tails and 1 to heads. And so of course you can like talk about, you know, these are your like 2 random outcomes, and you can talk about their probability of happening. And okay, let's kind of like continue with the example. So suppose you can have more than just like getting 0 or 1. Maybe you can get the numbers 1, 2, 3, 4, 5, 6, and this is going to map to your like dice roll. So okay, maybe let's just keep this example and just keep going by copying over things and stuff. So yeah, what's going to happen? Like your set of outcomes is going to change. And so let's change it. So your set of outcomes is now going to be 1, 2, 3, 4, 5, 6. Okay, which means I'm going to need to like assign some probability, some mass to these 6 points, and I'm going to need them to sum up to 1. And so like on a fair dice, I guess the story is going to be that like if you want to split the mass, the probability evenly across 6 points, you're going to have to assign like 1/6 to each one of these. And so, okay, maybe the masses now visually should be smaller, right? You got to like split it up into 6 parts, so maybe they're like this. And you know, you do the same thing for 2, 3. Oh, we are not using the number 0 anymore. So let's remove that. So you have 1, 2, 3, 4, 5, 6. Okay, and then I put like the exact same mass, which visually might look like this. And so I guess I'll write it like this. So like the probability or the mass of 0.1 is the same as the mass of the rod at 0.2 is equal to the mass at 0.3. Okay, and you get the point. It's the same as the mass at 0.6. And that's all 1/6. Okay, and wonderfully, like, if you kind of imagine that this function, let's say, can take in these like all these outcomes, you're going to need that the distribution somehow, or this like probability is going to sum to 1. So it's like p of 1 and 2 and whatever. And maybe I should have wrote it like, let's just go back to the heads and tails example. Maybe I should have wrote something like the probability of 1 or 0 plus the probability or the mass at 1 has to sum to 1. And so in this case, let's use our fun summation notation, right? Which is like the probability of the mass at point I. I'm going to need this to sum to 1, but I'm going to need it like I'm going to take I to be a number between 1 and 6. So I'm going to put I equals 1 to 6. I'm going to need that to sum to 1. And so you might already be recalling these are like the properties we told, or I told you that the probability has to satisfy, right? This is like the probability of all the outcomes is going to have to like sum to 1. Okay. And so, okay, so like we have this example. Hopefully this makes sense. It's kind of obvious. And so we might want to talk about, like the probability of like some subset of the outcomes happening, right? So like I might want to say like, what's the probability, of like getting 1, 2, or 3? Or in like physics world with this rod and masses, I would say like, well, how much mass is between 1 and 3? Or like on the points 1, 2, and 3. And so really I'd like a function, this like distribution, I really like it to like take in somehow like more than one outcome. And so we're gonna like want to do something like this. Let's say like, what's the mass of 1, 2, and 3? And so we're gonna say like, okay, like when we want to talk about multiple outcomes, we just like put them in a set. And this is really what we'd like our like probability to talk about, or our function that gives us the mass of the rod. So this is why like the probability is going to take in these sets of outcomes, right? And we're just going to call this an event. So this is like the event that you get 1, 2, or 3. Or in mass world, it's like, I don't know, the case where you have, or the mass between of 1, 2, and 3. Okay, so that's in general how things are going to work. And so we're going to need to take in sets. And to make this consistent, we're going to, like, all these things above should have really had like this set symbol around them. And that's why there's these sets, they're events. Okay. And you can see like naturally kind of like you can break out, as we saw kind of even above, is like the probability of this like should naturally be able to be broken up into like its parts kind of, right? And so this is kind of the other property, which is like, look at this thing. It's like the probability of a set, and you can think of this set as just like the union of a bunch of sets that contain the single masses or single points. And so this is going to be like the union of 1, the union with 2, and the union with 3. Okay, and naturally when you write it kind of in this way, and you can see that like, oh, these sets are what are called disjoint, they don't contain any similar elements, I should be able to like intuitively just talk about the, you know, the probability of 1 and plus the probability of 2 plus the probability of 3. That's what this should be. And that's exactly what the second property that we needed of this distribution is, which is that like the probability of disjoint unions is just the probability of the sum of them. So this will just be like probability of 1 plus the probability of 2. So that's the probability of 3. Okay, so we kind of like hopefully built up the beginning foundations, whereas like, you know, the outcomes, maybe I should tell you this, right? These are like your outcomes. It's like, you know, what can you expect to get? Or like, where is their mass? Right? These are the places where you can like, if there's no mass, you can't ever expect to get that kind of value. And then this object here, right? That's just some event. This is the naming. And we're going to want to talk about the probability of these events. And we informally sometimes say things like, you know, the probability of an outcome. But really we mean the event that just contains that single outcome. Okay. And so, okay, so now let's get into this like random variable thing. Like where does that sort of come up? And then we'll keep continuing with this example maybe. So your random variable is just going to be like a variable to describe the outcome you actually get. And so, yeah, we'll just write a variable symbol, and that, you know, it's like your random outcome based on your, let's say, roll of a dice here. And that random variable is going to take like, you know, a value between 1 and 6. Like if you roll the dice, you're going to get a number 1 and 6. You're going to use a variable to describe the roll of a dice. And so like, maybe it's more pleasant to write like things like this, which is like the probability, you know, that my random dice roll, that variable, is, let's say, like the number 3. Oh. Or you might want to say like, okay, what's the, you know, probability that my random dice roll is less than or equal to 3? And so largely speaking, we're going to think of this as like the motivation for these random variables. They describe this like random outcome, and we're going to want to talk about what's the probability that this random outcome like satisfies some properties, and like it's clearly more human readable, I suppose. It's like, what's the probability that my roll of a dice is 3? What's the probability that my roll of a dice is less than 3? And the natural mapping to like the mathematical formulation and stuff is just you map it to the corresponding event. So like this would be the probability of the set, and this is like the definition, I guess I put something like this, is like exactly the probability of the event that you get 3. And this would be like the probability of the set that contains numbers less than or equal to 3, right? So that's the thing we saw above. Okay, here we're going to get into like a nice property that we're going to see in a second, which is like, well, from above, you can see that, you know, this thing should be like it equals these things. And we just saw that, you know, these objects can be written as like the probability that your random variable takes the value 1 or 2 or 3. So we're going to have like this kind of thing. This is equal to the probability the random variable takes 1 or 2 or 3. Okay, so these are all kind of the same. And okay, we're gonna it's gonna become more formal when I get into the probability stuff, but you can already see that, there's a lot of events. Like I can write the set of 1, 2, 3. I can write the set 1, 2, 4, 1, 2, 5, and it would be kind of unfortunate if we had to define this distribution or this function for all those events. But you can see based on this property that you can break them up into these unions, you get this lovely thing that all you need to do is kind of define it for every outcome. So you just need to define what's the probability of the event that I get a single outcome and then another single outcome, and you just need to do it for all the outcomes. And then if you ever want to talk, well, I'll fix that in a second. If you ever want to talk about the probability of multiple outcomes happening, well, it's going to be sufficient to just say that that's equal to the probability of each outcome summed up. And that's going to, well, let me fix the lighting. So that's going to lead us to defining a new function called this probability mass function, which I haven't talked about yet. And that's kind of where we were getting to last class. And so it turns out that to define this probability distribution over an event, you're just going to need to talk about these single events. And we're going to call this object P of x equal to some little x, some function on its own. This is we're going to call this equal to little p of little x. And this object is just called the probability mass function. That's this object, this little p. And this thing actually takes outcomes. And it's mapped to be equal to exactly this. And the purpose of it is the following. If you ever want to talk about the probability of some event, it would be sufficient to just talk about the probability of every single outcome in that event, and then just sum it up. Right? So the above now is just little p of 1 plus little p of 2, and this thing actually does take outcomes, and it's naturally how you'd want to talk about things. So the probability of the event that you get 1, 2, or 3 is just this probability of 1, probability of 2, probability of 3. Okay. And so at this point, we get into some fun stuff. Okay, so you can see that I can kind of extend this story to any sized outcome space, right? I can just make it oh, you think this will work. So we're going to run into some troubles. So we want to make this outcome space, let's say, bigger and bigger. We want to add the number 7 and 8 and 9 and so on and so on. And if you do that, you're going to need this property that all the outcomes, the probability of all the outcomes is going to sum to 1, right? And notice that to describe the distribution, as we saw, all we need to do is kind of define this. So I just need to tell you what's the probability of every single outcome, and then I know if I sum that up, it's going to give me 1. And so we're going to do that for bigger outcome spaces in 1 second, but I just wanted to point out that right, in general, these things didn't all have to be 1/6. I could have chose a different value for them. Maybe I'll put it in purple so it's not confusing. Maybe I chose I don't know, 3/6 here. Well, now I'm constrained to the fact that, I need to allocate, I only have 3/6 mass or probability left, and I need to allocate it to the rest of the outcomes. So I clearly can't give them all 1/6, because otherwise we're not going to add up to 1. And so maybe I would say, okay, the probability of 2 is still 1/6. Okay, I got 2/6 probability left in my budget. Okay, maybe I still give this 1/6. All right, I still have, so now I've got my budget of 1/6 probability or mass left to allocate. And so maybe then I just give the other ones here I don't know, I need to break up 1/6 into 3 parts. Maybe I do it evenly. So I do 1/18, and then this one would also be 1/18, and then this guy would be 1/18. And if you sum these up, they'll give you 1. And visually, it would be something I draw the mass maybe above. So you got a bigger mass here. This is the 3/6 or 1/2. This one's still 1/6. This one's still 1/6. This one's tiny now, 1/18, 1/18, 1/18. Okay, but it satisfies this property. So you can see seems we're in good shape, to talk about probabilities. all we need to do is kind of tell you the probability of each outcome. So let's take this to kind of the extreme now. And let's say we want to talk about like, well, let's say the outcomes you can get are actually like any natural number. So like you can get 0, 1, 2, up to like as big of a number as you can think of. Are we going to be okay doing this? Oh, let's try it. So, okay, I just redraw things. So let's do this. So suppose my like random variable can take any outcome. And by when I say like it can take any outcome, that really means that I want every single one of these outcomes to have some non-zero probability. Because if the probability of it's 0, then like my random variable can't really take that outcome. So like the outcome space should be like all these things that can take non-zero probability. Okay, that's what we're working with. So that you want this to be like, let's say it can take 0 or 1 or 2 or whatever up to as big of a number as you can think of, which we called this the natural numbers, right? This is that set. Okay. So we have a rod. So far it's got no mass. And let's just say 0 is here so that I have more room to the right. And it needs to allocate, infinitely many points onto this rod. Can we do this? So let's start. So what's that going to mean? It's going to mean that the sum of I equal to 1. Okay, let's practice our notation here. So like this would be like the sum where let's say little n equals to an element of the natural numbers, right? And you sum up all these n's, so that would be like 0 plus 1 plus 2 plus 3 plus 4 plus so on. You can like equivalently write this as the sum that, let's say little n starts at 0 and goes to infinity. And you sum up n. These are the same. And like visually, this just means like 0 plus 1 plus, oh. Do we see a problem here? Right? I'm not trying to sum up the outcomes. The goal is to sum up the probabilities of the outcomes to equal 0. So clearly I made a mistake here. We're going to want to sum up, like, let's use the rule of PMF, right? We're going to sum up the PMF, the mass, the probability of each one of these, the mass of each one of these points, and we're going to want it to equal to 1. Okay, so just continuing with this notation. It's going to look like this. So the probability of 0 plus the probability of 1 plus the probability of 2 all the way ... Well, what's that going to have to equal? Our goal is to make that equal to 1. Okay. And so if you took calculus and you learned about, sequences and whether sequences converge, all that was talking about was whether a sum of infinitely many numbers, where the numbers can change with the indices, can they converge, whatever. And you might have learned that, yes, there's indeed infinite sequences, or like infinite sums that will like sum up to something that's a finite number and it's not infinity. And so, I don't know, let's take a question. Does anyone know of a sequence that converges to something that's not infinity? Yeah. Yeah, so I think you said something like add half of the last number. So I suppose like that will be written something like maybe n equals to 0 to infinity of like, let's say 1. Oh, okay, we add this one here, which I guess is like n. Oh. Okay, you need to pick like something here, I guess. So like you pick some like a, and then you take it to the power of n, and a has to be some number less than 1. And I think this is called like the geometric sequence, if I'm correct. And that will indeed give you something that's a finite number. Yeah. And a is less than 1. Because of course, if a is 1, then you have problems. If it's less than 1, then every time you raise it to a power, you get a number that's getting smaller and smaller and smaller. And if I recall, I think this sums up to something like 1 over 1 minus a, maybe. Okay, so that's one example. The example I was thinking of, and this one's totally fine. So we're gonna like, okay, well, what is it gonna tell us? It's gonna tell us that we can like assign a probability to each point n, a value of a to the n. And okay, we're gonna need this to sum to 1, so we're gonna then need to like normalize to make this 1. So okay, so if I want this to equal to 1, right? How do I do that? I go in the front and I'm like, oh, you know, this thing gives me 1 over 1 minus a. So how do I do that? I multiply the left-hand side by 1 over a. So then the right-hand side is going to be 1 over a times 1 over a. I get 1. And maybe to make this more visually obvious, if I move it inside the sum, this is just a constant, then what this is going to tell me is that my PMF for a given n should be the following. Right? And if I sum them all up, I'm going to get 1. And there's, you know, there's other sequences. Okay, so that should answer the question that we're in luck. We're cooking. So this guy here, like if you look at the 0.0, well, you're going to have, I guess here you allocate 0 mass to it because, actually you allocate 1. Okay, so maybe we need to start from like, I think this might be the sequence where it goes from n equal 1 to infinity. Okay, let me just solve this in a slightly better way so we have the same thing, which is to make that work, I'm going to do like n plus 1 here. And I think that's okay. Okay, so yeah, so what that means is at the point 0, how much am I going to allocate? Well, I'm going to allocate like 1 plus 0 times a to the power of 1. So I will allocate like mass a. And then here I'm going to allocate like, I guess at 1, I'm going to allocate some mass, which is like P of 0 equals a. P of 1, well, that's going to be 1. No, 1 minus a, and then a to the power of 2. And you do this on and on. I don't know, we get to like 100. Well, what's going to be the mass at 100? It's going to be like 1 minus a times a to the 101. And all these cases, right, a has to be less than 1, like strictly less. And so we're going to be in good shape. We're cooking. We got this thing. Everything works. And it turns out that even if our outcome space is, importantly, countably infinite, we are okay. Okay. So is there any questions about this before we try the next big leap, which is to make our outcome space uncountably infinite? Okay. So we're going to try this. And we're not going to do it yet, but we're going to just like say, like, suppose instead of the natural numbers, I chose the real numbers. So now I have like all possible numbers between 0 and 1 and between 1 and 2, like literally all the numbers, and I have the negatives and so on. Is this going to work? And the answer is going to be no and whatever and so on. We're going to run into problems. But before getting there, let's just get to the lecture like content to map what we've seen so far. And I want to mention one last thing, which is this type of object where, like, maybe I write this. Basically, if outcome space of random variable x is countable, and so what does countable mean? So countable means finite, as we've seen, like that case of 1, 2, 3, 4, 5, 6, or countably infinite, which is like the natural numbers. Then we give the random variable a name. And the reason we give it the name is because we can do the things that we've talked about so far. Then x is called a discrete random variable. Okay, so everything we've seen so far are what are called discrete random variables, and they're described by this property that they have this countable outcome space. And so talking about probabilities will be sufficient to just describe what's the probability of each outcome. Because then if you want to talk about any, like the probability of any event, like, I don't know, like let's say I want to talk about what's the probability of the event that is the set. Okay, so I'd write something like X, let's say is less than 100. Right, this is just like the event that the set containing 1, 2, 3, 4, 5, 6 up to 100. What's the probability of that? Well, that's the same as just summing up the probability mass functions, right, at points I, or let's use n because we've been using n, where n goes from 0 to 100. You just sum them up and we're good to go. So, yeah, so this is a very important point to note, is that to define the probability distribution of any event for a discrete random variable, all you need is this PMF, and you're good to go. And that's it. If you ever want to calculate the probability of something, you just need the probability of the outcome, sum them up, you're fine. Okay, and yeah, we're gonna have problems with x when x is uncountably infinite, and let's come back to that in a second. So let's remind ourselves of what happened now in this probability distribution stuff. So yeah, okay. So going back to the notes, like the rough story was, yes, there's these outcome spaces. Probability distribution is this map from events to numbers between 0 and 1, as we saw. And okay, there's these properties that are needed to satisfy. You can read through all these, and then like there's going to be these random variables, which we also talked about. And yeah, so all you're going to need to know for really is that discrete random variable, countable outcome space, so that you can just define the probability at each of these outcomes. And then there's going to be something called a continuous random variable. We'll come back to it in a second. And then we talk about how do we calculate the probabilities, and it's using these things called probability mass functions, as we talked about. So if you have a discrete random variable, so yeah, if you have a discrete random this discrete outcome space, which is, I should have put the word countable. In this countable outcome space, as we've seen, then your random variable like z that belongs to this can be described by this probability mass function. So like the probability that z is an element of any event, or you just sum up the PMF for all the outcomes, right? These are the outcomes in the event. Sum them all up, you get the corresponding probability. So this PMF is all you need to talk about the probabilities. And then it turns out people, give these certain types of distributions with certain outcome spaces names that they like to use to refer to them. And it turns out this coin flip case and like the fair dice and so on have like names for it. And so let's just go down. These names are called Bernoulli distribution for the flip of a coin. And a Bernoulli distribution is the following. It's always over an outcome space of two objects, so like 0 and 1, for instance. And then, there's all you need to do is describe the probability, which is the PMF, at outcome 1 and outcome 0. And people like to give these variables, like alpha, because if you notice for this case where there's only two possible outcomes, the probability of one outcome must be 1 minus the probability of the other outcome. And so it's sufficient to just give one variable. So you'd say something like, I have a Bernoulli distribution with parameter alpha. And this parameter will tell you everything you need to know. The parameter alpha tells you the probability of getting 1. 1 minus alpha tells you the probability of getting 0. And then you can calculate the probability of any other event. There's only two left. It's like the probability of 1 or 0 or the probability of nothing by adding these things up. And that's a Bernoulli. Turns out to come up quite a lot. And in the case of a fair coin flip, alpha was equal to 1/2. Right? Okay. And then the kind of other obvious one is like you sometimes want to talk about, the case where things are uniform or they are all the outcomes of equal probability. And so in this case, you'll have an outcome space that's like arbitrarily large. 1, 2, 3, up to n, could even be the natural numbers. It cannot. It can't be the natural numbers. Forget about that. Because like if it was the natural numbers, then it would be like, you have to give you'd have to give some number to all the natural numbers, and if you sum that up, that will not converge. So there's a problem there. Okay, so if your outcome space is finite, has n objects in it, 1 to n, well, then you can assign each of these n objects the same amount of probability, so like 1 over n. And then we say that some distribution is uniform with parameter n, which tells you everything you need to know. Tells you there's n outcomes, the probability of each outcome is 1 over n, and you've seen cases of this. If it's a dice roll, then n was 6, and the probability of each number was 1 over 6 for a fair dice. For a coin flip, n was 2 for a fair coin, and the probability of each thing is 1 over 2. Okay, so that's really all we need to know about these discrete random variables. Let's get into the case of the continuous random variables, which are these uncountable outcome spaces. So let's try working with that. Let's go back to the picture. Why not? Okay, so we want a random variable to take any number from the real numbers, which really what I mean by that is I want the probability of getting any real number to be non-zero. Okay, and I'm going to turn the lights back on. Okay, so somehow I'm going to need this to hold, right? Which is like, okay, this is actually not allowed to write. I'm not allowed to write this in math, but I will write it. Which is like, if I sum all the elements of the real numbers, and I plug these numbers, right? This is like the probability of each of these numbers, and I plug them into some, like, let's say I try to use this like PMF thing, and I plug it into this thing. I'm going to need this to sum to 1. Okay. So that's what I'm going to want. And this is going to tell me that, you know, everything's 1. And okay, and the other property, right, is that I want P of n to be greater than 0, strictly greater than 0. Oh, okay, maybe I won't use that symbol. For all n elements of reals. And it turns out this is not possible to do. There's no way to assign non-zero values to every element of the real numbers, and then somehow try to like accumulate them such that they will give you the total of 1. And so roughly speaking, you should think of the following. We go back to our rod. So now suppose you have this rod, or this infinite line, but you know, it's like, it's more realistic now, you know, it's not this thing where like, you have this like infinite, let's say completely like massless string or something, and then you put like point masses on everything. You know, in physics would be like, okay, in the real world, things are like continuous. You know, there's like kind of a mass everywhere. So maybe now I'll draw the rod without these like, okay, maybe I still keep these arrows, but I give it some kind of thickness to it, right? So now it's kind of got some mass everywhere. And the question is, can I like, is this going to be allowed? Like, can I really give it like a mass everywhere and so on? And so let's look at some things. So first of all, what's going to happen here? Why like I'm not going to be able to assign this. This is what I'm going to claim. I'm not going to be able to assign like the probability of any particular, the mass at any particular point to be greater than 0, right? So let me read this in mass form again. This says the mass at any point on the rod, I want it to be greater than 0, and I want that to be true for all points on the rod. And the kind of, I guess the intuition people give at this point is something like, what that means is that if I look at the rod, I can look at like intervals of it, right? So let's say this is 1 and this is 0. I can talk about like the mass, let's say for the interval 0 to 1. And well, okay, that might have some mass. I don't know, let's just say we assigned it like mass 1 over 6 or something, for whatever reason. And then I can zoom in further, right? I can say, look, okay, let's get smaller. Let's talk about the interval between 1 and 10, you know? So what's that? What's the probability of this set, right? This is an event. This is totally fine. This is a set. What's the probability of this thing? And maybe to be consistent, right? This is really, I should be using this distribution function here that takes in events. And you'll see notation like this, which is your random variable belongs to this. So it's the probability that, if I randomly get some number, it's going to be in this interval. So now it's the interval 0 to 1 over 10. Well, maybe it's evenly distributed between 0 and 1. So that would just be 1 over 6, but a tenth of that. So it'll be like 1 over 60 maybe for this example. Okay, and you can see as we're getting closer, we're going to try to shrink this interval more and more and more and more. And the claim is that for these, like where the mass is kind of like distributed literally everywhere, which means over all the real numbers, because that includes every single possible point, that if you look at any individual point in this rod, it has 0 weight. Okay, that turns out to be the claim. You can get smaller and smaller and smaller, and you can get as small as you want. And you give me any interval, like, okay, this is getting like more kind of like math theory stuff, but you give me like any interval, like A to B, and you tell me that whatever, you have like some amount of probability, like 1 over C, and that's like the smallest probability of anything. Well, I'm going to be like, well, I can make this interval even smaller, obviously, just shrink it by a little bit, and your probability is going to go down and down and so on. So anyways, that's the rough story of how this works. So with these random variables that can take on values in intervals or real numbers, there's going to be this really weird property now. Okay, here, look at this. So now I'm going to, okay, so what we just discovered is somehow, if I take the probability distribution, and I ask, is x equal to any particular number? Let's say a, or little x is usually used. Well, that's going to be 0. There's no mass at any particular value. However, still, like clearly the rod has some mass. And let's say the mass, the rod still has to have a mass of like 1 as before. And that's what we're going to want from probability. So that's to say that the probability of x taking any element of our outcome space, right, is going to have to equal 1. Okay, so for instance, this was like x taking any element of R is going to have to somehow still equal 1. Right, this is the whole outcome space. And this might, like, right, this seems kind of weird and so on. And so now I'm going to tell you how we deal with it in like physics world, and then it's the exact same mapping of how you deal with it in probability world. Okay, maybe let me just make this like a little bit more intuitive maybe. So instead of the reals, let's say instead I took like, I don't know, like the 0, 10, 6 interval, right? This is still uncountably infinite. You would still say this random variable is a continuous random variable. And visually it would look like this, which is my rod now is not, well, okay, sure, it's still infinitely long. But the places that I actually have like mass or thickness to the rod will look something like this. So it would be like, let's say the 0 to 6 interval. And the way I've drawn it here kind of now is like I've allocated a 1/6 of the mass to the first 1/6. And I mean, visually, it looks like I've allocated the mass evenly everywhere. And so that's exactly kind of what I was going for. So if this was like, let's say 5, then if this is evenly allocated, then this kind of region should have a mass or probability of also 1 over 6 and so on and so on and so on. So the question now is, what are we going to do? How are we going to define this probability distribution? If there's like infinitely many intervals, the intervals can have some mass, points can't have mass. And the solution we had before was like, oh, I just tell you, you can define this by just telling me the probability of any single particular location, right? And since it was countably infinite, yeah, you just tell me the value at all these points and you're good to go. But now this isn't going to work because the value is 0 everywhere. Okay. And so the solution, we say, is that there's no mass at points, but instead we can talk about the density. Okay? So this is going to tell you, roughly speaking, like how much, like, I don't know, mass is in some like region or something like this. And so if you take like the density, and you take you basically integrate the density, which is like, let's say like, kind of like accumulate the density over some region, you will get the corresponding mass. Okay. And so what we're going to have is something called like a probability density function. And so now the probability of like any event that we'll say is just like an interval. So like now if we want to talk about, let's say, the probability that my random variable is an element of some interval a to b, well, that's going to be defined as the integral from a to b of some probability density function. Okay. And we also use the little p for this, but when things are continuous, little p stands for the probability density function. And and so I integrate this region, and what I should get is the corresponding probability. So what does that look like? What that looks like is I look at this rod, and now I have some density at every point, and then that density is going to be kind of like, maybe the height of the rod, and I'm going to integrate, which is take the area in this region. So in this example, the height of the rod, if I gave it kind of like a y-axis, since things are uniform, I'm just telling you this because I know, and then you'll see that this works in a moment. Let me draw a better line. The height of this is going to be 1/6. So that's going to be the, this is going to be your p little x. P of little x. Right, this is like your x-axis. And so now I'm telling you the density is going to be 1/6. And this is going to be valid on the interval 0 to 6. Why? Because now this thing here, the probability that x, okay, now we change this to the interval. And the interval is going to be, the whole outcome space, so 0 to 6. How is that going to work? Well, that's going to have to now be equal to the integral from 0 to 6 of the density, so that's little p of x dx. Now let's plug in that density. Told you it's 1/6. Right? And now I suppose we do some very profound math and solve this integral. And that's going to be something like, 1, how do we do this? 1/6 is a constant. The integral of a constant is x. You then calculate it at its corresponding bounds, 6 and 0. And you get 1/6 times 6 minus 0. And we get our beautiful 1. And so this is great. And so this actually solves all our problems. And this would be called like a uniform density. And so now, here's the conclusion. You want to talk about the probability of random variables that can take like uncountably many things? Well, you're going to use densities. And the density, if you have the density, which beautifully is just like the PMF, a function of outcomes, but it's not to be read as the probability of x. It's now to be read as the density at x, right? You can now calculate the probability of any event by just integrating over the density, like integrating this density over that region. And maybe like finally, just like a little more trickier example is like, okay, well, imagine x is an element of, the interval, 0 to 1 union. This would be called like I guess a disjoint interval, union 5 to 6. Okay, well, the way you do this is, let's do it very formally here, which is you would say, okay, I need to integrate, and this is like the general way of writing integrals. I need to integrate my values of little x that belong to the set 0, 1, union 5 and 6. Let's say that, and then you have to integrate p of x dx. Okay, and then beautifully, integrals are what are called linear, so you can break them up, right? The integral of these like disjoint regions is just going to be the sum of the integrals. And so this will just simply be the integral from 0 to 1 of p of x dx plus the integral from 5 to 6 of p of x dx. And then you do that, and for our example above, that would be like 1/6 plus 1/6, which is 2/6. And that, once again, gives you exactly what you would expect, right? If you have like this uniform density, then if you take 1/6 of the mass, or the rod, and you take another 1/6 of the rod, You add them up, you get 2/6 mass of the rod, or 2/6 of the probability. Okay, and at the end of the day, what you're going to need to know is this is how you calculate your probabilities of different events. You're going to do this in the assignment. And you just need to know, if I tell you that, and this is what you should expect to be given this, which is someone tells you the density of your random variable, and then you go ahead and do all the calculations just using that density through this integration process. Okay. And I guess at this point, I take some questions. Yeah. So the density of the rod is the same as, like, we should think of it kind of like as the height of the rod here. And so but the mass, right, will be kind of like the area in the rod. Yeah. So it is not to be thought of as the, the probability or the mass at the point. It is just to tell you how dense it is. And maybe like I can draw a slightly different rod, maybe in purple, and we'll see this kind of rod. Okay, this is a terrible drawing. But maybe I distribute it like this, so I've taken like a bunch of mass from here, and I moved it up into here, and I've taken it from here and moved it also up into here. And my claim is going to be that the area, right, this is what this whole integral from 0 to 6 thing says. It says that the whole area under here must be 1. And so I have to distribute it in such a way. Yeah, so if someone says, like, you have a random variable, and they ask you to calculate the probability of something, and they don't tell you the density, you tell them, good luck. Like, I have no idea how to do it. Like, there's no, the problem's wrong, or like, I can't do it. So you should always be given the density if you want to calculate some probability for continuous random variables. Okay, and as with these discrete random variables, there are some classic densities, I guess, or random variables that have certain names, right? And the names are given due to their outcome space and their density. And before, we had names of discrete random variables which were given due to their outcome space and their corresponding PMFs. And that's the other part of these continuous random variables. So continuous random variable, it's a random variable that takes values in an uncountable outcome space, and the probability of any single outcome is 0. And we saw that kind of works. And so then there's the probability density function, as we saw, which has the property that the probability that your random variable belongs to some event is just the integral over that event. And that will always be really intervals in our class. Here, let's do another fun thing that you'll probably need to know. Imagine I added here the union with the set exactly the number 4. What will be the probability of this thing? Right, so all I've done is I've changed the event to not be like the 0, 1 interval, union 5 and 6 interval. I now added one more thing to that set, which is just the number 4. Now, what's the probability of this event? Yeah, so basically, yeah, the answer is it will be the same. What's going to happen? Well, what's going to happen is you go here, you're like, oh, okay, let me just move some things around slightly so that it's not so visually cluttered a little bit. So this thing is 1. Okay, so now if we look here, right, we had like the sum of the first region, sum of the other one, and we can actually talk about the integral, right, on this interval, which is the interval from 4 to 4. And so that's going to look like we add an extra plus here, and that's going to be the integral from 4 to 4 of p of x dx, which you might have learned in calculus is just equal to 0, no matter what p. Oh, well, maybe not. Let's just say, like, for any p that has a finite value at x, this integral will give you 0. And then there's some weird stuff that happens where people define it to be kind of infinite, and that's called like a Dirac distribution and so on. But for our course, it doesn't matter. Okay, so yeah, if you take a small enough region, which is, as we saw, like basically the probability of that outcome, right? This is the probability. Let's try it one more way. This guy here, what's this? This is the same as the probability that x equals exactly 4, and we've seen that's 0. So there's all sorts of ways you can think about this. Okay, great. And that, if you understand that, you're in really good shape to kind of do a lot of things. Okay, what I didn't finish explaining was classic names of continuous random variables. Okay, there's as we had seen with the rod, there's the case of the uniform random variable, but it's not a continuous uniform random variable, or sometimes we'll call the continuous uniform distribution. And so this is the case where your outcome space is like some region between A and B. A and B must be finite, like A must be a number and B must be a number. And then you just distribute the density evenly across everything. So in the case where this was like, 0 and this was 6, what we saw is this density must be 1 over 6 minus 0, so 1 over 6. Right? And so people will say, okay, well, like before, you just need 2 parameters now. Or someone will be like, and so, okay, so in like questions, you might see something like your random variable follows a uniform distribution with parameters A and B written like this. So your the distribution of your random variable is uniform A, B. And this is enough for you to do things because you know that this distribution has a density which is equal to the following. And all you need is the numbers A and B to know what that density is. Okay. So you might not be directly given the density, but you will need to know that the uniform distribution has that density. And you're going to be given this on the formula sheet, don't worry. So your formula sheet on your exams will tell you that like uniform this tells you or implies that the density is like 1 over B minus A. Okay, the lights are off again. All right, we're almost at the fun stuff, which is talking about like the probability of getting a data set soon. And now I tell you about another classic continuous random variable first though, or distribution. And that is the normal or Gaussian distribution. And that is the distribution that has a PDF, right? The beautiful thing is when you talk about a distribution, you can now characterize it fully by its corresponding PDF. And so what's the PDF, the probability density function? Well, it's this really weird looking complicated object. But roughly speaking, it's just like an exponential function, kind of squared. So like, you take the negative and the right, and exponential kind of looks like this or something, but now you squared it, so it smooths it out. And it's going to turn out to look like what is called a bell curve. So people call this the bell curve. I don't know. I guess some profs curve exams using the bell curve or your marks. And yeah, this is what it looks like. And now let's just understand this picture so you don't get confused. When we draw, like things like this, let's understand that it's not that the distribution is a bell curve, it's that the density is this bell curve. So we're drawing here little p. This is the density. It can actually take as input, outcomes. And so I think in here I use the random variable z, so like it would take in like outcomes little z. And it'll tell you the density of the thing. And it's just kind of like with the rod example, it's like I've kind of moved the mass from the outsides of the rod to the inside, like this. And the beautiful thing is here, you actually don't need your outcome space to be like this interval. It can actually be all the reals. And you can make it such that there's like tiny, like it's still like the density is still something all the way out here. And the mass will also be something if you take the area, but it's like minuscule, it's so small. And it turns out, yeah, so if you integrate, I guess I never wrote it anywhere, but based on the properties of a distribution, if I take the integral, or like if I want to know what's the probability, that z belongs to the real numbers here, well, that must be 1, and that's going to be the integral, right, from like you write a negative infinity to infinity of, p of z dz. And if you want an exercise, you plug this thing in, and you calculate the integral, and you will get the number 1. And that's, okay, roughly speaking, how does this work? How do people define it? Like, well, okay, maybe like you integrate this function, you get a number. And then guess what? People are like, oh, that number seems to be way too big, right? So that's not going to sum to 1. Maybe it's like some number. And guess what that number is? That number is exactly this, 1 over that. So then you divide by that, so you get a sum of 1. So this is called like how much you need to normalize to get a sum of 1, or the integral to be 1. Okay, and then there's another distribution which is very similar to this normal distribution, which is called a Laplace. And really the only thing that changed is the exponent now has been changed to be not squared, but absolute valued. Okay, and I just realized I forgot to mention something very important, which is that similar to the other distributions, there's going to be like parameters that kind of tell you everything you need to know about it. And in particular, everything you need to know about how to calculate the corresponding PDF. And so we'll say things like, your random variable has distribution that is Gaussian or normal with parameters mu and sigma squared, which have very important names. They're called the mean and the variance, or the expected value and the variance. And that'll be enough because this PDF is only determined, like it's fully determined if you plug in mu and sigma squared. That's all you need to know to calculate that function. So once again, if I tell you something like your distribution is Gaussian, that means, oh, I know now that the PDF is this with these values plugged in. So I could give you something like, you know, and this is the common symbol it's also used. So I could say something like, I don't know, this 0, 1, totally fine. Tells you the mean is 0, the variance is 1. This turned out to have a special name. And I guess to be consistent with all the stuff is I make this green so you don't get confused. What happened? And this has a special name. I don't know if you need to, but just so you know, it's called like a standard normal. And these parameters have a very important interpretation, right? Which is mu is going to be kind of like the mean or the average value, and it's going to be like the center of this density here. And when we get to expected values and averages, you're just going to see that that's like the average kind of value you get if you randomly, whatever, gather data using this distribution. So one example, what's normally distributed, like heights. It seems that like if you gathered a survey on people's heights, you'll see something like this actually, in terms of its like density. And you will find that, I don't know, this mu will be like the average height. So maybe for males, it's like, I don't know, like 1.65 meters or something like this, or 70. And then sigma squared is called the variance. And as the word indicates, we'll see it in a second, or like a little bit later, it tells you how much, like how wide, how much does it vary relative to the mean. And so this density here, that's not as kind of wide, that doesn't vary as much, it will have sigma squared, which is much smaller than this green one, which has a density that is quite wide and it has a lot of variance. And then like in intuitive terms, what that would mean is that the probability of you getting some value farther from the mean is more likely, because in the green one, there's more mass for larger values than there is for this orange one, right? And that's exactly how you calculate the probabilities. Okay. Beautiful. And the Laplace, literally almost the exact same thing, except now you put an absolute value here. Its parameters mu is also its mean and b is the variance. Same exact interpretation, just looks different than the Gaussian, but like, yeah. Beautiful. Hopefully I built a better foundation than last lecture about how things work. And now we can start getting into the fun stuff, which is like trying to define this random data set. And notice that this random data set kind of has a lot of like things going on. You know, it's this big, long tuple of all sorts of objects. And there's like, you could say that maybe the first house I gathered, you know, the first information about the house, that's like one random point. Maybe you call it a random variable, which we will. And then you gather another house and its price, and that's going to be another like random variable. And then the third one, and so on. And so that would be like maybe an equivalent mapping to this house. Well, like to give you maybe some intuition, it's like I flip one coin. I flip a coin once. That gives me a random outcome. I flip a coin the second time. That's another random outcome. And a third time, and a fourth time. And it turns out that you might want to talk about what's the probability, you know, that like 4 coin flips are some value. So like that would mean like what's the probability that the first coin flip was 1, and the second was 1, and the third was 1, and the fourth was 1. And unsurprisingly, we're going to have random variables that contain multiple random variables, which are called multivariate random variables. Because they, yeah. All right, so I talked about the motivation kind of examples are like, you might want to say, what's the probability I get heads on a coin? And then the other random variable maybe is like rolling a dice and getting a 3. And then for the case of houses, it's like I might want to ask like, what's the probability of like, if I get, you know, a single house Then it has 4 rooms and 2 washrooms, and it's less than 10 minutes from the university. So it'd be like a case where you have 3 random features. Okay, and then the example we're going to use as kind of the running example for like these notes is that what's the probability that someone is young and has arthritis? So you're going to have like a random variable for, you know, the probability of being young, and another random variable for if you have arthritis or not. And we're going to start talking about all sorts of questions like, what's the probability that you're young? Well, what's the probability that you're young and have arthritis? Or what's the probability that you just have arthritis, and so on. And these all have special, you know, distributions to calculate them and so on, but hopefully you get the point of where we're going here. Okay, so how do we formulate this in our framework that we've seen so far? Well, it should be supernatural. If you flip 2 coins, what are the possible outcomes you can get? Well, naturally, they're going to be described by like an ordered pair, or like I guess it's just the pair, right? Where the first index is going to mean the value of the first coin flip, the second index is going to mean the value of the second coin flip. Now we see these Cartesian products, very useful, right? Like, look at this. This is what I want my outcome space to be. It's going to be like, I get 0, 0, or I get 0, 1, or I get 1, 0, or the outcome's 1, 1. Beautiful, I can write it like this. This is the Cartesian product, as we've learned before. And that's your outcome space. It just contains all possible outcomes. And then everything's literally like the same story. We're just gonna have like nicer notations and so on. But like, you know, this will be, you can have like a random variable for this outcome space. Since there's finitely many things, we'll call it a discrete random variable. Yeah, like this. And then the story's gonna go the same. Okay, and so for the house case, I guess this is important to know, is, yeah, so suppose in the house case, you have like 2 random things that you want to talk about, like the number of rooms and the age. And then you want to talk about every, like, what's the case of all these outcomes? Well, it's going to be this Cartesian product, which is ginormous, right? It's like this set of all possible pairs where the first index is any natural number and the second index is any number from 0 to infinity. And yeah, that's very big. There's going to be uncountably many of them. And so this would be like a continuous random variable, because there's already uncountably many of values in this thing. So you're going to have at least as many as that in your corresponding outcome space. And you can make this even bigger. Like this was the case with what we call 2 features, right? You can have 3 features, like number of rooms. Oh, sorry. This is going to be like the case where you have a feature label pair now, right? So you can have the number of rooms, the age, and then the third outcome is going to be like your price. So this is really, now we're getting into what it really looks like. So if I gathered a house, which meant that I got the number of rooms, the age, and the price for that house, I would have like, I mean, the description of the house, that would mean that's my outcome. That's my random outcome. And then I have a random variable like z, which is described by, like I can write like this, where like x and y, where x is this thing, and y is this, or sorry, x is my random variable, y is my random variable, and they're going to belong, so, okay. X, it's an element of this guy. Y, it's going to be an element of this guy. These are my 2, and then I can group them together and so on. Okay, so important terminology. If I have a random variable, like let's say let's just do the house thing. If I have a random variable describing the first feature, x1, and another random variable describing the second feature, x2, and another one for like the labels. When I group them like this, and I could have like, for the purposes of this, remember there was this one-to-one correspondence with tuples inside tuples. So I could have also wrote like x1, x2, y. When I group them like this as a tuple where order matters, right? I will give that sometimes, like usually you'll call that another label, and you'll say that this is a multivariate random variable, because it's a random variable that's a tuple of many other random variables. And so this would be the case for one single random feature. And then you can imagine what the data set's going to be. It's going to be like n of these grouped. So it's going to be this like, you know, this giant multivariate random variable. It's going to have n multivariate random variables in it, where each one of those n multivariate random variables looks like kind of like this. Okay. So let's continue the story. of how do we work with these objects and now talk about things since we have like different random variables and so on. And we're going to do this all with this, I said, arthritis and being and your kind of age example. So yeah, this is an example. Having arthritis and if you're young or old. So I characterize this. Now we're going to try to like formulate this English thing that we want to talk about into a mathematically consistent notation. So what are the possible outcomes I can get? Well, for this, age part, if you're young or old, I'm going to have an outcome space which is going to be described by 0 and 1. So 0 will be young, 1 is old. We're going to have another outcome space for arthritis and no arthritis. No arthritis is 0, 1 is arthritis. And then as we saw, this thing, when you expand it using the Cartesian product thing, you're going to have this set, right, that contains like 0, 0. That's one outcome. That will mean that I'm young and don't have arthritis. Then you can have 0, 1, which means I'm young and I have arthritis. This is old and don't have arthritis, and old and I do have arthritis. So you got your full outcomes. And then the story goes the same, right? This is going to be a random variable, which is this tuple that contains these two different random variables. And you would write you have x, which is a random variable that's an element of 0, 1. And y is also a random variable that belongs to the outcome space 0, 1. And these numbers have this meaning that we talked about. And guess what? Since we have a finite outcome space, everything goes the same way, kind of. You need a PMF to talk about the distribution, right? Or, you don't need to, but it's way nicer. And so then you're just going to have a PMF that tells you the probability of each outcome, and that'll be sufficient to talk about any other event because you can just take sum them up. Okay, now there's 4 outcomes, so there's many ways we can visualize this that will be very helpful for downstream questions we have. So I can write it out mathematically. I just need to tell you the PMF evaluated for a particular outcome, what is that value? There's 4 outcomes, so I've decided on some numbers that we're going to use in this example. The probability of, and sometimes this is how it's written as well. So, right, this is an outcome 0, 0, and when you plug in a tuple inside a function like this, people will often just remove the brackets and just write it like that. It's totally fine. Okay, so probability of 0, 0, 1/2. Probability of 0, 1, 1 over 100. Probability of 1, 0, 1 over 10, 1 and 1 is 39 over 100. The important thing, you just chose any numbers that sum to 1. And now let's look at the visual intuition. This gives out a lot. So you can draw maybe as a table of what this function, right? This is your PMF function. These values inside are P of x, y. And so, yeah, if you look at 0, 0, the probability of that outcome is 1/2, and so on. Maybe the more intuitive one is to draw it with corresponding kind of masses that we've been doing before. So now you have a 2D object that you're kind of allocating regions of mass to it. So this whole thing has let's say area of 1 or mass of 1. And you need to break that up into 4 parts. And the way we chose to do that is to break it up into 1/2 for the 0, 0 point, I guess, 1 over 10 for 1, 0, 39 over 10, and whatever. Okay, great. And yeah, that all sums to 1. And now, given this, we can ask all sorts of useful questions and calculate it very easily, such as the following. What is the probability of being young? So that would mean just x equals 0. So we'd write something like that. We're what's the probability of x equals 0? And that is to be interpreted as the event, right, where the first outcome is 0, x equals 0, or young, right? That's what that means. And the other thing, the arthritis thing, you don't care about it. So what that means is you take all of the outcomes that have x equal to 0, but the other thing can be anything. So you will just literally sum them up. And there's various, you can write it in this Cartesian product notation or whatever. Yeah, so people will write things like this, that what's the probability that x equals 0 and y is anything else? That's how you would calculate this. That, of course, is just some event, as we've seen, above here. So you just calculate that thing. What does it look like? Well, it turns out that, if you write it out, it's the probability of all the outcomes in the event. And then you calculate, You sum the corresponding probabilities of all those outcomes. Well, you could just write, I mean, this is like this thing, right? This sum. This is you getting used to this double sum notation. I guess I only highlighted how single sums maybe work, but you can just sum over multiple variables, and it's like you sum the inner one, and then you sum the outer one once the inner one's been calculated. And so this summation notation, well, it's exactly the same as saying like some z belongs to the event, right, which is 0, 0, and 0, 1. Okay. And so, yeah, you do this whole thing. You get what you would expect. It's the probability of being young is just the probability of being young and not having arthritis plus the probability of being young and having arthritis. You add them up and you get 51 over 100. Okay. So let's end there, and then next class we'll pick up with where we ended off with. All right. Have a good weekend, everyone.